All right. You guys can hear me well, right? All right. Welcome back. Today is September the 21st, and boy, just like that, summer is gone. I'm gonna start missing summer. I feel like COVID just stole spring, now stealing summer for me. So, well, not just for me, for everybody. All right. So sad. And fall fall is fun, but it's one of those seasons where kind of like makes you sad sometimes. 'Cause seeing all the leaves falling. I prefer winter than fall, honestly, because fall depresses me a little bit when I start seeing all the trees losing their leaves. Um, that's like a sign of death to me. Although the days are beautiful and gorgeous and cool and crispy, um, it's just depressing, I think, to see the leaves fall. But the on the other hand, the colors of the trees change, so it's kind of nice. But once I get into winter, I get already used to seeing, all the trees barren. But after that, it's it doesn't affect me much, and I enjoy the cold weather. So, but my favorite two seasons are spring and summer. But if I had to choose one of the two, it's gonna be definitely summer. All right. So let's get started, guys. I think you can see my screen now. Um, and please stop me, interrupt me anytime. I just want to, guide you through this chapter. We're going to start chapter 5 today. Chapter 5, mainly, we're going to be covering two things. We're going to be talking about degrees of unsaturation and what does that mean and why is it important. Um, then look at these problems. These alkene problems are so easy compared to what you guys are used to now. We have already done E and Z and R and S for alkenes. So I will not touch this because we spend a lot of time. And so then we're gonna go just to reaction coordinate diagrams. This is important, believe me. I mean, you will see this again. Of course, in this class. And if you were to take like a standardized test, like the organic chemistry ACS, this kind of questions will be there because honestly, this is how reactions work, and you want to understand how something works in order for you to make sense out of it. And so this reaction coordinates, and there's only like 4 cases, which is good. But there's so much we can learn from these 4 cases, and you will see why. And so we're gonna touch on that, and pretty much those two topics: degrees of saturation and reaction coordinate diagrams will be what we're gonna be talking about here. All right. So just a quick overview here. Degrees of unsaturation, also known as DU, or other books calls it Index of Hydrogen Deficiency, IHD. And so basically the degrees of unsaturation measures any ring present in the molecule, any double bond, any triple bond that is present. And so as you can see here, you can determine the DUs at first glance. So notice that this is 1, 2, 3, 4. This is butan 1-ol or 1-butanol, and the degrees of the saturations are 0. This diene 1,3-butadiene, and I better hurry up because this diene has 2 double bonds, so it has 2 degrees of unsaturation. This other molecule, this is cyclohexene, cyclohexene has 2 degrees of unsaturation, has the double bond and the ring, so that's 2. this other, this is an amide. This is an amide. This amide has 3 degrees of unsaturation. 2 on the triple bond, because you have 2 pi bonds, and 1 more pi bond in the carbonyl. So you have total of 3. This ring that you see here on the right side is the famous benzene ring. Benzene has 4 degrees of saturation, 1 the ring, and 3 double bonds, so that's a total of 4. All right. How do we measure DUs? So DUs are expressed here. DUs is the maximum number of hydrogens minus actual number of hydrogens divided by 2. All right, so how do we calculate that? So the formula for degrees of unsaturation, you need to memorize it. It's not that difficult to memorize it. And I put this little brain here. When you see that little brain there, that means that you had to memorize it. All right, so here's the formula, 2n plus 2. What does that remind you of? Anybody? What does that formula reminds you of? Just this part.
That for the hydrogens that it holds?
Yeah, for the alkanes, remember that? Yes, exactly. So we said that the number of hydrogens, so the formula for alkanes was 2n plus 2 when it comes to hydrogens. And so notice that we have 2 times n plus 2 minus x divided by 2. So where n stands for carbons in the molecule and x is the number of actual hydrogens. All right, so check this out. So what are the effects of the atoms on the DU? So for the oxygen, it's none. For the halogens, they count as actual hydrogens. So they increase the value of x by 1 for each halogen. So x now then becomes the number of hydrogens and halogens in the molecule. That is your actual number of H's. And then nitrogen increases the maximum, I mean the left side of the equation, by 1. And so your formula becomes 2 times n plus 3. Plus 3, because if you have 1 nitrogen, that nitrogen will be able to bond 3 times. And that's why it becomes 3. All right. And so I have an example here where I had C7H14Br2. Notice that then the formula, I don't have any nitrogens in the formula. On this one I do have one on the right side. But on the one on the left I have 2 times 7, 2 times n is 7. That's 14 plus 2, that's 16. 16 minus 16 is 0. 0 divided by 2 is 0. And so I ask you to write an example of these molecules, and I just put 7 carbons, 2 bromines, and the rest will be hydrogen. So we have 3, 2, 5, 7, 9, 11, 12, and then 2 more here will be 14. For the case of this formula on the right side, we have C8, H9, NO. We find that the degrees of saturations are as follow. So we had 2 times 8, that's 16, plus 3, we have to change to 3 because we have a nitrogen, minus 9, divide all that by 2. So 2 times 8 is 16 plus 3, 16 plus 3 is 19, 19 minus 9 is 10, 10 divided by 2 is 5. And that's, so to put an example, So I have 5 degrees of saturation. One easy way to, when you have 4 or more degrees of saturation, you will most likely have a benzene ring. In this case, I chose to put a nitrogen in the ring. That's what I could come up with. Put the nitrogen on the ring, and then from the ring we have 4 degrees of saturation. This ring is a pyridine ring. Spells Pyridine, pyridine. And so it has, the ring is 1, and the 3 double bonds are total of 4, and then the double bond on the carbonyl, that's 5. So this molecule will fit this degrees of saturation. Now, for those of you who need to take the second part of this course, you will know that when we start the second semester, the first thing that you're going to have to require to do is degrees of saturations. Because in spectroscopy, you need to know that. Because in spectroscopy, we're going to be dealing with determining the structure of, for example, of an unknown or a formula, and we're given the spectra. And so the first thing you need to calculate is the degrees of saturation, so you know what kind of functional groups you're dealing with. So if you have a double bond, most likely you could have a carbonyl group. Or if you have 4 degrees of saturation, then you know you have benzene ring. And so you can compare your benzene ring now to the signals that you have, and then you can confirm your structure. All right. So then I had some more examples here. We're gonna do these examples in today, and we're gonna skip the naming of the alkenes because we are more advanced than this problems here, honestly. We're gonna go right into the reaction coordinate diagrams, fast and slow, exergonic and endergonic. And so in my recordings, I took a lot of time explaining this. So I'm gonna give you a summary. So you have 4 options. And you learned this in GChem 2, I'm pretty sure, because this is all physical chemistry. And the only physical chemistry that I like to do, honestly, is like lifting objects. Well, lifting chemicals, and mixing them up, that's physical chemistry. That's enough physical chemistry for me. But this thing, though, is fascinating, though. I mean, I want you to understand how a reaction pretty much behaves. A reaction cannot think, but we're going to think as one. All right? So the diagram on the top left, A, represents an exergonic reaction, because the delta G of formation of these products, it's actually lower in energy. You notice that if you trace a line here with the free energy on the left side, this coordinate is lower in, the products are lower in energy than the reactants. So when you subtract products minus reactants, you get a minus delta G. Delta G is the free Gibbs energy, and it calculates the energy in a system. And it refers to delta G is equals to delta H, which is the enthalpy. Enthalpy, in a few words, is the amount of heat in the system in a reaction. And so delta G becomes equals to delta H, enthalpy, minus T, which is the temperature of the system, multiplied by delta S. Delta S is the entropy of the reaction. And entropy, in a few words, is nothing but the amount of chaos or disorder that the molecules have. Notice that when the molecules are inside of a flask, let's say you have a flask full of hairspray, a can of hairspray. Inside of your hairspray can, you don't know, while you're sleeping, while you're like eating, while you're like doing your normal activities, inside of that can there's a bottle of collisions, and those molecules are constantly moving until you release some of that hairspray into your hair. But inside of the can you have collisions that are elastics, so you get one one molecule hitting another one, and just like you're playing pool, you hit one and then it goes off, and maybe hits another molecule after the collision. And then you have the decomposition collisions where two of them meet head to head, and they don't bounce back anymore. They just get destroyed. And that's why eventually your hairspray will, with time, will decay. So it has an expiration date. So please check the expiration date if you want to make your hair look good, because that's important. Because otherwise you will have nothing but decomposition material being sprayed onto your hair, and sometimes it's just pressurized air at the end when it comes out, because most of the chemicals are already decayed. And it's because of the collision. So that is your order of entropy, or your amount of disorder and chaos. Basically is disorder in the universe. And I'm going to get a little philosophical here. Every reaction vessel that you have, when you make a reaction, that's a universe. Your head, your brain, your mind is a universe. Only you can think of things different than others people. And this university, that's why they call universities, because each university is a university, right? Where you have like famous people here, you have your athletes, and you have your famous profs, and the not so famous people. All of that is part of this universe. And everybody knows that. Everybody knows in this universe where the cafeteria is, where the library is, and where the bookstore is. So that's the entropy. That's the entropy, the order, the level of disorder in a universe. And so now, if you look at this equation, delta G of free Gibbs energy is equal to delta H, which is enthalpy minus temperature multiplied by entropy. The way chemists have figured out how to control the reactions is by slowing them down, by slowing down the entropy or the level of disorder by cooling the reaction down. So when T it's 0 or like minus 80 degrees, it makes the entropy really, really small. It makes it negligible, to the point where you have like molecules like moving really, really fast. Imagine like I am moving my hands really, really fast right now, and all of a sudden, I start moving my hands slow because the temperature is controlling the entropy. And so that's really cool. So let's go back to our diagram. So now you have an idea, and that's why we sometimes heat reactions, sometimes we cool reactions, because it has a purpose. And until you get to this thing, you don't know the purpose, right? I want you to know the purpose. So next time we're heating a reaction in the lab, notice that we're going to be overcoming this hump called activation energy. All these humps or bumps are activation energies, and we need certain degrees of heat. Now, reactions behave differently. Check this one out, the first one on A. So when the reactants wants to turn to product here, the transition state is right here at the top of the hump, and this hump is really, really small. We say that this reaction is fast and it's unstable. Another thing we can say from this reaction is hot, because the delta G is negative. When the reaction is hot, it liberates heat, therefore it's exergonic. All right. So it's similar to when you sweat. When you're sweating, you're actually cooling your body down, but you need to liberate heat. So your sweat, because your body is so warm, your sweat is liberating heat. Your body starts like, I mean, if you see a spectrum of your body when you're running and you're really, really hot, you will see fumes coming out of your head. You will see, oh, like you can see that in the winter. There's like fume coming out of our heads or our bodies, and then we start sweating. The sweat kind of cools off. It's meant to cool our body off because we're so warm. We are in an exergonic state at that point. And so our bodies are hot. So is this reaction. And this reaction will be fast because it has a small hump. Now, it's unstable. Why do you think it's unstable? Because it wouldn't take that much energy to reverse this reaction, because the hump or the transition state is very low. And so I imagine this reaction, this on A, as if you were to like jump a small obstacle, like you're jumping a rock or you're jumping a small branch. That's a small jump. That your jump, you're gonna be from the ground back to the ground really fast. All right. Now let's take a look at B. B is also hot because delta G is negative and it's exergonic. Another term that you will hear, and is interchangeable, is exothermic. Exo means it's outside, the heat, it's an outside thing, event. And then thermic comes from thermal, or means temperature. So the temperature gets lost to the outside of the system. All right. So a reaction vessel is a system, and it's a universe that is happening inside of that flask when you're mixing something. All right. Now, this reaction is slow because your transition state is really, really high. Imagine now you are rock climbing. So now it'll take a long time for you to come from the ground all the way up to back to the ground again. And so because the reaction is slow, it's steady, it's also stable. So okay, so that's exergonic. So on the right side, we have the opposite. We have an endergonic reaction, because now the products, the delta G of the products, the delta G is the total change in free gives energy. It's different from the products minus the reactants. Then you get a plus delta G. When you get a plus delta G, your reaction becomes cold. If you take, let's say, if you take something like ammonium chloride, which is a solid, and you dissolve that in water, that solution will turn really, really cold, like ice cold. And it's because the reaction is exergonic. Is endergonic, and heat is being absorbed. So now you know that cold is the absence of heat, right? Just like Albert Einstein used to say that hate is the absence of love. All right. So that's and therefore he even went on to say, this is Albert Einstein said this, which this is why I respect him and admire him. He said that if there is then God, there must be an evil, because evil is the absence of God, right? And so, um, and he explained that basically based on the amount of heat or the absence of heat when it's called absorbed in molecules. All right. So that's a really cool analogy, I thought. And so notice that this reaction here is also fast. Your activation energy is small. It has a small hump or bump. And your delta G is so if because it's so fast and so small, the activation energy, it becomes unstable. Notice that these two on the top are unstable, and it'll be easy to overcome this reaction back into the reactants. And so the reaction will be reversible. That's why it's unstable. And it's endergonic or endothermic because it's absorbing heat. So instead of liberating it, it's absorbing it up. So what the reactions do is when they get cold, they're actually absorbing the heat from the surroundings, and basically from air or water from the air. And as you can see that your flask will become, frozen. Water will stick around the flask in the form of ice, just to feed the heat that reaction requires. All right. And so likewise, you have a slow, stable endothermic or endergonic reaction on D, because now your delta G is plus, the products are higher than the reactants, and your activation energy is high. So you need enough energy. You need a lot of energy here to overcome. And so I make, in my videos, on my recordings, I make the analogy of a pole vaulter. The pole vaulter runs, then he puts the pole, and then he starts flying and jumping with the pole. He has enough time to, check out the temperature in the atmosphere there on the top. He checks that, his hair looks good on the fall. He has enough time to even call his mom, and then he lands on the mattress. Because the activation energy is so high, he has time to do all that. The jump is absolutely long, and it takes time. He also needed to prepare enough momentum to put the pole vaulter here, put the bolt and start, put the pole and start flying over the activation energy. Which is an energy barrier, basically. So this is what it says here. The free energy of activation is the energy barrier of the reaction. If you don't apply enough force or enough heat, you will not overcome this hump, and therefore the reaction will go up to here, and if it doesn't have enough energy, goes back to the starting material. You never made the reaction. All right. So those are the 4 examples that we're going to study. We're going to see that we're dealing with, for this synthesis, for this reaction, we're dealing with bond breaking and bond making. And that's why chapter 6 will be challenging for you. I'm telling you, there are 3 chapters that will define your will define you this semester, and they will define your grade. Chapter 2, which you already have mastered, I think most of you have a good understanding of acid bases. The second most difficult will be chapter 6, because In chapter 6, we're going to start doing reactions. And you haven't done that. Well, the type of reactions we're going to be doing are bond making, bond breaking. You are used to reactions in GChem where you're switching counter ions and balancing each other out. So these reactions with organic chemistry are a little more challenging because, like I said, it's bond breaking, bond making, bond breaking. All right. And so one thing you have to keep in mind is that transition states also, these transition states are imaginary. They are real, but we cannot prove them because you cannot isolate them. That's the problem. But we know that they exist because without them, we wouldn't be able to explain the reactions. But they're totally imaginary. All right. And so if we look at this reaction coordinate, one thing you have to learn is what's happening. So you have to, if you're just giving a reaction you have never run, at least you need to know how to dissect it, how to explain it. And so if I'm giving this reaction, I see that I have a higher bump than another one. So every bump represents a reaction. Every top part of the bump represents a transition state. Every valley represents a product. Or in this case, on the left side will be a reactant. Represents a compound, let's say. So you notice that we have two reactants here, the alkene and the HBr, which is hydrogen bromide. We're going to have a transition state before it forms this. And this in this molecule here in the middle is the reaction intermediate. So this reaction has two steps, has one intermediate, and it has two transition states. Each bump has a transition state, and each bump represents a step. All right. Now, the rate limiting step has its transition state at the highest point of the reaction coordinate diagram. So between these two bumps, I can say with confidence that my rate limiting step or my rate determining step, that's another way to refer to it, is the step with the highest bump. All right. And I went on to explain that here. Well, when I used to teach this, I gave these examples. We're going to have those examples on the practice homework. All right. So we're going to head over there. Is there any question up to this point that you didn't quite get? So if there's no questions, by all means, let's begin the practice homework. Practice homework number 5. Here it is. And I'm going to teach you some things that it's not there in the notes, but you can only know them by doing problems. Because that's what we do. We solve problems. We are the solution. We have to be the solution to the world. And so solving problems is part of that. All right. Number 1, calculate the degree of unsaturation in the following formulas and then draw as many structures as you can for each. All right. So this is an interesting mental problem. Let me find a cool pen here. All right. So notice that we are given this structure. This molecular formula. We're going to find structures. So du stands for this one will be 2 times n is equals to 4, plus 2, right? Because we don't have a nitrogen, minus the number of X. The number X is the number of hydrogens and halogens combined. So we have how many? 8, right? Divide all that by 2. And so what do we have? 2 times 8, 2 times 4 is 8, plus 2 is 10. 10 minus 8 is 2. 2 divided by 2 is 1. All right. So notice that we have 4 carbons. So let's do this. So what if I have 4 carbons and a double bond? That would be 1 degree of unsaturation. That's 1. Notice I have 1, 2, 3, 4 carbons. I have 3, 6, 7, 8. I don't have a hydrogen here because that carbon is happy. It has 4 bonds. But I have 2 methyl groups. That's 6, and 2 hydrogens that are terminal here on this alkene. So that makes it 8. Another possible structure will be this 1, 2, 3, 4, or this 1, 2, 3, 4 with a double bond. How about this? A cyclobutane fits. That has 1 degree of unsaturation, 4 carbons, and you have 2, 4, 6, 8 hydrogens. One more. How about this? A cyclopropane with a methyl group. How super duper cool is that? I think that's as many as I can come up with. Let's do the next one. Or who has this one?
It's 2.
It's 2. Very good, Grace. All right, so it's 2 times 4. We have 4 carbons, plus 2, minus 6. 6 is the number of X, divided by 2. 2 times 4 is 8, plus 2 is 10. 10 minus 6 is 4. 4 divided by 2 is equals to 2. So now we have 2 degrees of unsaturation, and we have 4 carbons. I'm going to start with this one. 4 carbons and 1 degree of unsaturation, 1 double bond, that's 2 degrees. So this will be C4H6. So I have 2, 4, 5, and 6. So I have 6 hydrogens there. I'm just gonna get rid of these hydrogens because I want you to get used to like just linear structure. Check this one out. Look at that. That will have a lot of strains. So that's a cyclopropene with a methyl group. Check this one out. What if I have 2 cyclopropenes fuse? Whew. That will make a really, really good detonator. Imagine the amount of strain in that thing. And then this one, an open chain one, 4 carbons and 6 hydrogens. So I have 1, 2, 3, 4, 5, 6 hydrogens, which I'm going to delete because I want you to get used to seeing that and thinking and counting them mentally. All right, do I have any more? Yes, we do. How about this? Cyclopropane with a double bond. That's 2 degrees of saturation. Or how about this? A triple bond with 2 methyl groups. That's 2 degrees of saturation. I could do the same thing and move the triple bond again. And I have 1, 2, 3, 4 carbons and There's a hydrogen here, and then there's 2 and 3 here. That's 6. How cool is that? Let me get rid of these little dots. So it'll be triple bond in ethyl. And how about this one? Do you think this is different than the previous one that I drew there? Yes, the methyl is on the double bond now. This is as many possibilities that I can think of. All right, let's do the next degree of unsaturation. C3H4. So this is how much we got. Anybody had done this math already? 2. Very good. Who said that?
Me.
Who was me?
Megan.
Who?
Megan.
Megan. And what's your last name? Macy?
Massey.
Massey. Megan Massey. Very good. All right. Good job. So you come up with this, and you said, okay, 2 times 3 is 6 plus 2 is 8. 8 minus 4 is 4. 4 divided by 2 is equals to 2. All right. Check this one out. We have, how about we did this? We have a carbon with a double bond and then 2 CH2s on the ends. This is called Q mean, because the double bonds are accumulated, so they call them Q means. This is another possibility. Cyclopropane with a double bond or a triple bond with a CH3 group. You have 3 carbons, 1 here at the end, 1 here, and the methyl group. And then you have 4 hydrogens. All right. Calculate the degree of unsaturation in the following formulas. I want to get to E, so E is the most interesting one. What time is it? Oh, we have 6 minutes. We can do this. So du is equals to 2 times 6. Check this out. Now we have a nitrogen. We have to add what? 3, according to the formula. Plus 3 minus 5. We only have 5 hydrogens. We're going to divide all that by 2. So we have 2 times 6, 12, plus 3, 15. 15 minus 5 is 10. 10 divided by 2 is 5. All right. We're not going to do examples on that one. We're just going to do the math. I want you to get used to the math. The next use will be 2 times 6 plus 3. We have a nitrogen. Minus 5. We have 1. We only have the x's are 5s, are 5 hydrogens divided by 2. Oh, that's exactly the same thing I had on the top. Notice that the oxygen did absolutely nothing to it. That's an example, so you can see that oxygen doesn't really affect the DUs. Now this one is interesting. C8, so it's 2 times 8. We don't have a nitrogen, so it's plus 2. And
That's 9.
I'm sorry?
Is it supposed to be... Where did 8 come from?
Right here, 2 times n. 2 times 8.
Okay.
2 times 8 plus 2 is the number of bonds on carbons from hydrogens. Minus how many? What is the number of x here? Anybody?
12.
12. Very good. Who said that?
Trinity.
Trinity. Awesome. So 12, because we have 9 plus 3. Hydrogens and halogens count as 1. Excellent. So we divide all this by 2. And what's this result going to be? Like 2 times 8, 16 plus 2, 18. 18 minus 12 is 6. 6 divided by 2 is 3. All right. All right. Next one. 2 times 9 plus 2 or 3? 2, right? Because we don't have a nitrogen. Minus how many? 18. Very good. And divide all that by 2. So that it takes us to 2 times 9 is 18 plus 2. That's 20. 20 minus 18 is 2. 2 divided by 2 is 1. All right, we're going to do the next one. This is cool. Check this out. You have 2 nitrogens. All right, so you're going to do 2 times 10 plus how many you think you had to add?
4.
4, very good. So you add 4 because if it was only one nitrogen, you add plus 3. But if you had one more nitrogen, you had to add 1 extra one. Because in the end, this number cannot be 2, but it needs to be even. So that's why it's plus 4. Yes.
I had a question about the. Well, I guess you answered it. Never mind.
You got it? Okay. I'm gonna explain it. I'm gonna explain a little bit more here. So I'm gonna subtract what? 12, right? The number x is 12. There's no halogens. And divide all that by 2. And I'll get 2 times 10 is 20 plus 4 is 24. 24 minus 12 is 12. 12 divided by 2 is 6. And so I'm gonna write a note here. Let me write a note.
Why didn't you do anything with the oxygen?
Oxygens don't change anything, remember? It says in here, oxygen has no effect on DU.
Oh, okay.
Remember, and also, if you look over here, this example had 2 oxygens, and the formulas are similar. You see that C6H5N versus C6H5NO2, and the oxygens did absolutely no effect on the DU. Now, let me put a note here. They are 2 nitrogens. Thus, the formula two n plus 3, you add 1 more to become 2n plus 4. All right, I think that's all we have for today. We'll cover the rest between Wednesday and Friday. On Wednesday we'll have a quiz. It's gonna chew up most of the time, so we'll have like 20 minutes for this class on Wednesday, but which we have time. All right, guys, I will be seeing you soon. Study for the quiz. I'll see you on Wednesday. Have a wonderful day.